Tonight, we will talk about something very far away. Something that does not rush. Something that does not make sound. Black holes. They exist quietly in the universe. They do not shine. They do not announce themselves. They simply remain patient and distant. As you listen, there is no need to understand everything. There is no need to remember anything. Just let the words pass by slowly, like thoughts before sleep. Black holes are places in space where gravity is very gentle, yet very strong. Not in a loud way. Not in a violent way. But in a calm, constant way that never stops pulling. They are not holes in the usual sense. They are not empty. They are filled with mass that has settled into a very small space. So small, that even light moves quietly around them. Most black holes are born from stars. Very old stars. Stars that have finished their long, steady lives. When their light fades, what remains slowly becomes something quieter. A black hole does not chase things. It waits. If something passes close enough, gravity gently guides it inward. No sudden movement. No rush. From very far away, a black hole feels like any other object in space. Its gravity behaves normally, calmly, predictably. They can be small, or very large, but they all share the same patient nature. They grow slowly, over long periods of time. Black holes do not move quickly through space. They travel the way stars do, slowly orbiting, quietly following the shape of their galaxy. Some black holes sit at the center of galaxies. They stay there for billions of years, holding their place, doing nothing in a hurry. Time behaves differently near a black hole. Not in a way you would notice right away. Time simply slows, very gently. From far away, nothing seems unusual. Everything looks calm, everything feels still. Black holes are cold places. Not warm, not bright. Just quiet, and dark, and patient. As you continue listening, remember that these black holes are very far from you. They cannot reach you. They do not affect your night. They exist somewhere else, silently, while you rest. Black holes are very far from Earth. So far that their presence is only felt through quiet signs. A slow movement of nearby stars. A gentle bend in light. Nothing about them is loud. Nothing about them demands attention. When matter moves close to a black hole, it does not fall suddenly. It drifts. It circles. Slowly, patiently, as if deciding where to go. This slow movement forms a soft, glowing ring. Not because the black hole shines, but because the surrounding space responds. Calmly. Even here, nothing happens quickly. Everything takes time. Black holes do not grow fast. They take in small amounts of matter over long periods. Years pass. Then centuries. Then much more. Most of the time, black holes remain quiet. They are not feeding. They are not changing. They are simply there. Space around a black hole feels stretched. Not torn. Just gently pulled. If you could watch from a safe distance, you would see slow motion. Stars moving slightly differently. Light taking a longer path. Nothing would feel rushed. Black holes do not erase things instantly. They take time. So much time that from far away, everything seems almost still. The universe is very large. Black holes are only small parts of it. They do not dominate space. They quietly share it. Many black holes spend their entire existence unseen. No light. No activity. Just silent mass resting in space. They do not need attention. They do not need to be observed. Even now, as you listen, countless black holes exist without doing anything at all. They are not events. They are conditions. Slow, steady, unchanging. Distance protects everything. The universe leaves plenty of space. You are here. They are far away. Nothing crosses that distance tonight. Black holes remind us that the universe does not hurry. They exist on timescales that feel almost endless. While moments pass for us, they remain unchanged. Near a black hole, time moves differently. Not in a dramatic way. Just slowly. So slowly that change becomes difficult to notice. If a clock could rest near one, its ticking would feel softer, more spaced out, as if time itself were taking a deep breath. From far away, everything looks normal. Nothing appears broken. Nothing feels wrong. The universe continues calmly. Black holes do not interrupt space. They become part of it, blending in quietly. They do not glow. They do not flash. They simply remain present. Gravity near a black hole is not a sudden force. It is a constant one. Always there. Always patient. Objects nearby adjust to this pull. They change their paths slowly. Without resistance. Even light responds calmly. It bends. It curves. It follows the shape of space. Nothing struggles. Nothing resists. Black holes do not have surfaces. There is no solid edge. Just a gentle boundary where space behaves differently. Crossing that boundary is not an event you would hear. There is no sound. No signal. Just quiet continuation. The universe does not react. It does not pause. It does not respond emotionally. Everything remains steady. Black holes are not destinations. They are not goals. They are simply outcomes of time and gravity working together. Long before humans existed, black holes were already there. And long after, they will continue to be. They do not age in ways we recognize. They do not decay quickly. They wait. Silence surrounds them. A deep, unbroken silence that stretches across space. Even their influence travels slowly. Nothing arrives suddenly. Nothing surprises. As you listen now, time continues its gentle movement. Seconds pass without effort. Breathing remains easy. Somewhere far beyond this moment, black holes remain unchanged. Unaware. Unconcerned. They do not notice attention. They do not respond to curiosity. They simply exist, quietly, patiently, as the universe rests around them. Black holes are never alone. They exist among stars, dust, and empty space. Everything around them moves in calm paths. Slow curves. Wide circles. Stars do not rush toward black holes. They continue their orbits. Patient. Stable. From a distance, nothing feels unusual. Space behaves as it always has. Quietly. Black holes follow the same rules as other objects. They travel with their galaxies. They drift along invisible paths. There is balance in this movement. Nothing pulls too hard. Nothing escapes too quickly. The universe prefers calm arrangements. Black holes fit into these arrangements without resistance. Even when matter approaches, it does not fall straight inward. It circles. It waits. These slow circles can last for a very long time. Longer than any human lifetime. Longer than memory. Black holes do not seek attention. They do not announce their presence. They remain quiet centers of gravity. Space itself adapts around them. Stretching gently. Settling naturally. There is no border you could point to. No clear line. Only a gradual change. From far away, black holes feel ordinary. Their gravity blends with everything else. Distance softens all effects. Space gives room. Time gives patience. Most black holes will never interact with anything at all. They will spend their existence in stillness. No movement. No change. They are reminders that not everything must happen. Not everything must move. Some things simply remain. As you listen, your thoughts can slow in the same way. There is no need to arrive anywhere. No need to understand fully. The universe allows stillness. Black holes reflect that stillness back into space. They are not endings. They are not beginnings. They are quiet states of balance, and balance does not demand attention. It rests. Black holes may feel mysterious, but scientists understand them gently. Not all at once. Slowly. Over time. There are different kinds of black holes. Some are small, formed from single stars. Others are much larger, resting quietly at the centers of galaxies. The largest ones did not appear suddenly. They grew over very long periods, gathering small amounts of matter, patiently. Black holes are not invisible because they hide. They are invisible because they do not produce light. Light does not escape from them, so nothing shines outward. Yet scientists still know they are there, by watching nearby stars, by noticing gentle changes in movement. Stars near a black hole move differently. Their paths curve. Their speed changes slightly. These movements are calm signals, not warnings, just quiet information. Black holes do not pull everything nearby. Only things that come very close feel their full influence. Distance keeps space peaceful. Most black holes spend their lives doing nothing. They do not absorb constantly. They wait. Some black holes slowly release energy. Not through light, but through tiny, quiet effects that take immense time. This process is so slow that the universe barely notices. Black holes also help shape galaxies. Not by force, but by balance. Their presence keeps stars moving in steady patterns, preventing chaos. In this way, black holes support order. Silently. They are part of the universe's structure. Not outsiders. Not mistakes. Everything that formed them followed natural rules. Gravity. Time. Space. Nothing was rushed. Nothing was broken. Black holes do not end the universe. They exist within it, following the same quiet laws as everything else. Even now, scientists continue to learn by watching patiently. No sudden discoveries. Just gradual understanding. And understanding does not need excitement. It grows slowly, like the universe itself. Black holes do not exist in space alone. They gently shape the space around them. Space near a black hole curves. Not sharply. Smoothly. Like a slow bend in a wide road. This curve guides movement. Stars follow it. Light follows it. Nothing is pushed. Nothing is forced. The closer something is, the more noticeable the curve becomes. But even then, change remains gradual. Scientists describe this as space responding to mass. Not reacting suddenly, but adjusting calmly. Black holes are strong examples of this idea. They show how space and gravity work together. Even far away, their influence fades softly. Space returns to normal. Black holes also move. They are not fixed points. They drift along with their galaxies. As galaxies slowly turn, black holes turn with them, sharing the same long journey. There is no central control, no direction given. Everything follows natural paths. Some black holes have companions, stars that orbit them quietly. These stars do not rush inward. They remain stable for very long times. Their light allows scientists to notice the black hole's presence. Not directly. Only through quiet patterns. Black holes do not need to be seen to be known. They leave gentle marks on motion. Even the largest black holes remain calm. They do not tear galaxies apart. They help hold them together. This balance keeps galaxies shaped and steady, without effort. Black holes do not seek growth. They respond only when something comes close. Most of the universe keeps its distance. And that distance keeps everything peaceful. As you listen, space continues its slow movement. Galaxies turn quietly. Black holes remain where they are. Part of a much larger calm system. They are reminders that strength does not require noise. And influence does not require motion. Everything can be powerful, and still. Black holes help scientists understand the universe more clearly. Not through sudden discoveries, but through patient observation. They show how gravity behaves when mass becomes very dense. How space responds when weight gathers slowly in one place. From black holes, scientists learn that gravity is not a pull alone. It is a shaping of space itself. A gentle guiding of movement. Black holes also help explain why galaxies remain stable. Their presence influences how stars move, keeping large systems balanced over time. Without these quiet centers, galaxies might drift apart or lose their shape. Black holes teach that extreme conditions do not always mean chaos. They can also mean order, structure. Scientists study black holes by watching nearby matter, gas and dust that move calmly around them. These movements create patterns. Slow, predictable patterns. From these patterns, distance can be understood. Mass can be estimated. Time can be measured differently. Black holes also help test ideas about time itself. Near them, time moves more slowly. This confirms that time is flexible, not fixed. This idea is not abstract. It has been measured, observed quietly. Black holes also help scientists understand how stars end their lives. Not with drama, but with transformation. A star does not disappear. It changes form. Its mass remains. Black holes are reminders that nothing truly vanishes. It only becomes something else. Even information is not lost easily. It becomes difficult to reach, but it remains part of the universe. Black holes also influence the future of space. Over immense periods of time, they slowly change. Some will grow slightly. Some will remain unchanged. Some may slowly release energy in almost unnoticeable ways. These processes take longer than imagination allows. Longer than thought. Black holes are not endings. They are long chapters in the universe's story. They exist alongside stars, planets, and empty space. All following the same rules. All moving calmly forward. As you listen, this knowledge does not need effort. It can simply rest in the background. Understanding can be quiet. Learning can be slow. The universe does not rush its lessons. And neither do you. Black holes are not frozen in time. They change. But they change very slowly. Over extremely long periods, black holes will not remain exactly as they are. They will continue to exist quietly, while the universe around them grows older. As stars fade and galaxies drift apart, black holes will remain patient, unmoving. They will outlive stars. They will outlast planets. They will persist long after light becomes rare. Scientists believe that black holes are among the longest-lasting structures in the universe. They do not burn fuel. They do not rely on light. They simply remain, because gravity holds them together. Even so, black holes are not truly eternal. They change on timescales that feel almost endless. Over immense stretches of time, they may slowly lose energy. Not suddenly. Not noticeably. This process happens so quietly that it does not disturb space. It does not create sound. It does not create light. The universe barely notices. As this happens, black holes will grow smaller. Very gradually. This change is so slow that billions of years pass without visible difference. Eventually, far in the future, black holes may fade away completely. Not with an event. Not with a signal. But with silence. No explosion. No collapse. Just a gentle release of energy, spread across unimaginable time. By then, the universe itself will be very different. Cooler. Quieter. Most stars will have faded. Most motion will have slowed. Black holes will be among the last things to change. They will not resist. They will not struggle. They will follow the same calm rules that created them. In this way, black holes are part of the universe's balance. They appear. They remain. And eventually, they fade. Nothing is rushed. Nothing is forced. Even endings are slow. As you listen now, remember that these events are unimaginably far away. They do not belong to this moment. This moment is quiet. This moment is safe. The universe continues calmly. And so can you. Black holes help connect many ideas in science. They bring together gravity, space, time, and matter. By studying them, scientists learn that these ideas are not separate. They move together. They depend on one another. Black holes show that gravity affects time. Time does not move at the same pace everywhere. It slows where gravity is strong. This is not theory alone. It has been measured carefully. Repeatedly. Black holes also show that space is not empty in the way we imagine. Space has structure. It can bend. It can stretch. Mass tells space how to curve. Space tells matter how to move. This relationship explains motion without force. Objects follow paths because space guides them. Black holes are extreme examples of this relationship. They make these effects easier to notice. They also help scientists understand limits. How dense matter can become. How gravity behaves at its strongest. From this, scientists develop ideas that apply everywhere else. Even here. Even now. Black holes also connect the very large and the very small. They link galaxies to particles. Time to mass. They suggest that the universe follows consistent rules. Even under extreme conditions, nothing is separate. Nothing is isolated. Black holes do not break these rules. They follow them completely. This is why they are valuable to science. Not because they are dramatic, but because they are honest examples of nature. They do not hide information. They display it quietly. By watching black holes, scientists refine their understanding of reality. Slowly. Carefully. Each observation adds a small piece. No single moment explains everything. Knowledge grows the same way black holes do. Gradually. Over time. As you listen, this understanding does not need attention. It can exist in the background. Like gravity. Always present. Never loud. Black holes remind us that the universe is not chaotic. It is structured. Calm. Even its most extreme objects follow quiet rules. And quiet rules allow everything to continue without effort. Black holes are discovered without being seen directly. They do not reveal themselves with light. Scientists find them by watching their surroundings, by observing how nearby stars move. When a star orbits something invisible, its path reveals hidden mass. This mass does not shine, but it influences motion. Over time, these small changes become clear. Some stars move faster than expected. Some curve in unusual but stable paths. These calm patterns suggest the presence of a black hole. In some regions of space, gas moves in slow spirals, not falling inward immediately, just circling patiently. These spirals can be measured. Their speed, their shape. From this, scientists estimate how massive the black hole is. Black holes are also found through quiet disturbances in light. When light from a distant star passes near a massive object, it bends gently. This bending changes what observers see. Stars may appear slightly shifted, or briefly brighter. These changes are subtle. They do not draw attention. They require patience to notice. Black holes can also be detected by calm signals from space. Not sound, not light, but faint waves created when massive objects move. These waves are extremely soft by the time they reach Earth. They do not disturb anything. They pass through space silently. Detecting them requires stillness, sensitivity, time. From these signals, scientists learn about black holes that are very far away, on the other side of the universe. Even then, nothing feels urgent. Nothing feels loud. Black holes share their presence only through quiet influence. And that influence is enough. Many black holes are not alone. They share space with stars, gas, and dust. Some stars spend their entire lives orbiting a black hole. They do not fall in. They do not rush. They move in slow, predictable paths. Year after year. Century after century. These stars behave calmly, as if the black hole were just another object in space. From their movement, scientists learn how strong the black hole's gravity is. Not by force, but by rhythm. Some black holes have clouds of gas nearby. This gas does not disappear instantly. It drifts. It settles. As it moves, it warms slightly, not enough to be dramatic. Just enough to be noticed. This warmth produces soft light. Not from the black hole, but from the gas responding to gravity. This light is steady, quiet. It allows scientists to map the space around the black hole, to understand its size, its influence. In some systems, two black holes orbit each other. Very slowly. Their movement takes enormous amounts of time. They circle in wide paths, losing energy gradually. This slow dance can last longer than civilizations, longer than memory. When they move, space responds gently. Ripples travel outward. These ripples are extremely weak by the time they arrive here. They do not shake anything. They do not disturb rest. They pass through Earth without being felt. Black holes also interact with their environment by shaping motion. They guide. They influence. But they do not command. Most of the time, black holes remain silent companions, present but unnoticed. They allow surrounding systems to continue naturally. Nothing is forced. Nothing is hurried. The universe prefers cooperation over conflict. Black holes follow this preference quietly. Black holes do not produce light. Yet they teach a great deal about it. Light near a black hole behaves differently. It does not travel in straight lines. It follows the curve of space. This bending of light is gentle, gradual, predictable. When light passes close by, it may change direction slightly. To an observer far away, this light appears delayed. Nothing is lost. Nothing disappears suddenly. Black holes show that light has a relationship with gravity. Gravity does not pull light. It reshapes the space light moves through. This idea helps scientists understand how light travels across the universe. Not just near black holes, but everywhere. Black holes also teach about energy. Energy near them is not released quickly. It moves slowly. Gas that drifts nearby warms gently. It glows softly. This glow is steady. There is no sudden flash. No burst. Energy changes form without disturbance. Some black holes are surrounded by disks of matter. These disks rotate calmly. Their movement is smooth. As they rotate, they release small amounts of energy. Even this energy spreads quietly. Over time, this process can influence entire regions of space. Not through force, but through consistency. Black holes also reveal limits. They show how much energy can exist in a small region. How space responds without breaking. These limits help scientists refine physical laws. To understand what is possible and what is not. Even in extreme environments, rules remain consistent. Black holes do not violate natural order. They express it clearly. They demonstrate that complexity can remain calm. That power can exist without noise. This understanding shapes how scientists view the universe, not as chaotic, but as structured and patient. Black holes also help explain distant cosmic light. Light from far galaxies travels for immense time. Its path bends slightly along the way. These small changes carry information. About mass. About space. About history. Nothing about this process is hurried. Light travels steadily. Space guides it gently. Black holes are part of this guidance system. Not obstacles. Not interruptions. They participate quietly. As you listen now, energy continues to move calmly throughout the universe. Light continues its long journey. Everything follows its path without urgency. Black holes also help scientists think about information. Not messages. Not thoughts. But the basic details that describe matter. When something moves near a black hole, its form changes. Its position changes. But the universe does not lose track of it easily. Information does not disappear suddenly. Instead, it becomes difficult to reach, hidden behind distance, behind time. This idea helps scientists understand that the universe keeps records, quietly, without effort. Black holes suggest that space itself stores information, in subtle ways, through structure, through boundaries. Nothing needs to be remembered actively. The universe holds everything naturally. Black holes also show that order can exist without control. There is no central system managing motion, no direction being given. Yet everything follows consistent rules. Matter moves where space allows. Energy spreads where time permits. Black holes follow these same rules. They do not override them. This makes them valuable for understanding balance. They show how extreme conditions still respect structure. Scientists use black holes to test ideas carefully. Slowly. Over many years. No single observation is enough. Understanding builds layer by layer. Black holes encourage patience in science. They change slowly. They reveal themselves gradually. This mirrors how knowledge grows. Black holes also help explain why the universe does not collapse. Despite immense mass, space expands. Distance remains. Balance is maintained naturally. Gravity pulls. Space stretches. Time adjusts. None of these act alone. Black holes sit within this balance. They do not disturb it. They participate in it. They are reminders that even the most intense objects are governed by calm principles, no exceptions, no shortcuts. Everything obeys the same quiet laws. As you continue listening, this order does not need attention. It exists whether noticed or not. The universe continues calmly. Rules apply silently, and black holes follow them, without resistance. Black holes change how scientists think about scale. They show how large the universe truly is. Even the biggest black holes are small, when compared to galaxies, and galaxies themselves are small, within the full size of space. This perspective helps keep everything calm. Nothing is overwhelming. When seen in context, black holes also remind us that distance matters. Most objects in the universe are far apart. This distance keeps interactions gentle. Nothing collides suddenly. Nothing rushes. Even when gravity is strong, space provides room. Black holes rarely interact with anything at all. They exist in regions where space is wide, quiet. Most of the universe will never come close to one. And that is normal. Scientists also learn about time through black holes. Not time measured by clocks, but time experienced differently in different places. Near strong gravity, time slows slightly. Far away, time flows normally. This difference does not create conflict. It is simply how the universe operates. Black holes show that there is no single universal pace. Everything has its own rhythm. Stars age slowly. Galaxies evolve gradually. Black holes persist quietly. Through all of it, they do not mark moments. They do not define eras. They exist across them. By studying black holes, scientists gain humility. They see how brief human time is, and how patience is built into the universe. Black holes also help refine measurements. They serve as reference points. Stable. Reliable. Their steady presence allows comparisons across space. Across time. This consistency is valuable. Nothing about black holes demands urgency. They invite careful thought. As you listen now, perspective can widen gently. There is no need to focus tightly. Everything fits into something larger. Black holes are part of that larger picture. Quietly. Without asking to be noticed. Black holes act as quiet teachers in the universe. They do not explain themselves. They simply exist. By observing them patiently, scientists learn how nature behaves. Without interruption. Black holes show that gravity is not a sudden force. It is a steady influence. Always present. This influence shapes space gently. It guides movement, rather than commanding it. Near a black hole, space curves more noticeably. But even here, the change is smooth. Nothing snaps. Nothing breaks. This smoothness helps scientists trust their understanding of physics. Extreme conditions still follow the same rules. Black holes also help clarify the relationship between time and gravity. Time is not fixed. It adapts. In regions of stronger gravity, time passes more slowly. This effect is subtle. It does not create confusion. It creates consistency. The universe remains ordered. Even when conditions vary. Black holes also help scientists study motion. Objects move differently, depending on how space is shaped. Paths are not chosen. They are followed. This explains why orbits remain stable. Why systems last for long periods. Black holes do not disrupt this stability. They support it. They also teach that energy transforms quietly. Matter drifting nearby warms slowly. Energy spreads evenly. No sudden release. This behavior appears across the universe. Black holes simply make it easier to observe. Black holes are also reminders of limits. There is a maximum way space can bend. A maximum density matter can reach before behavior changes. These limits help scientists refine theories. They define boundaries that nature respects. Black holes also provide insight into how stars end their lives. A star does not vanish, it changes state. Its mass remains part of the universe. This continuity supports a calm view of change. Nothing is truly lost. Nothing truly ends. Black holes also encourage long-term thinking. Their lifetimes extend beyond imagination. Processes near them take millions of years. Sometimes far more. This slow pace is not empty. It is full of information. By studying black holes over decades, scientists gather consistent data. Small changes. Repeated patterns. Understanding builds gradually. Black holes also demonstrate cooperation between cosmic forces. Gravity, space, time, and energy work together. No single element dominates. This cooperation creates balance. Balance creates stability. Black holes exist within this stability. They do not stand outside it. As you listen now, this knowledge does not demand effort. It can remain in the background, like gravity itself. Always present, never loud. The universe continues its slow rhythm. Black holes continue their quiet role. Nothing is urgent. Nothing is missing. Everything unfolds at the pace it was meant to. Some black holes are known by name, not because they are special, but because they help scientists learn patiently. One such black hole rests at the center of our galaxy. It is called Sagittarius A star. This black hole has been observed for many years. Stars move around it in slow, predictable paths. Their orbits are calm. By watching these stars, scientists learn how much mass lies at the center of the Milky Way. Not by seeing the black hole, but by noticing gentle motion. Sagittarius A star does not pull stars inward. They continue their orbits peacefully. Nothing dramatic happens. Another well-known black hole is called Cygnus X1. It exists in a distant part of the galaxy. This black hole shares space with the star. The star slowly gives off material. This material drifts toward the black hole. As it moves, it warms slightly. It produces soft light. This light allowed scientists to confirm that Cygnus X1 is indeed a black hole. Even here, nothing is rushed. The process is steady. There is also a very large black hole called Messier 87 star. It rests at the center of a distant galaxy. This black hole is massive. Yet it remains calm. Its presence helps hold the galaxy together. Stars continue their slow movement. This black hole became known because scientists captured a soft image of its shadow. Not a picture of the black hole itself, but of space bending around it. The image was quiet, blurry, gentle. It showed how light curves near strong gravity. Another black hole, called V404 Cygni, has been observed during periods of activity. Even then, changes happen over time. Not suddenly. Scientists watch carefully. They wait. These named black holes are not exceptions. They follow the same rules as all others. They are studied not because they are dangerous, but because they are consistent. They provide reliable examples of how gravity, space, and time interact. Each named black hole adds a small piece of understanding, not a full picture. Just one quiet detail. Together, they help scientists confirm that the universe behaves the same everywhere, no matter how far away. As you listen, these black holes continue their steady existence. They do not notice observation. They do not change because of attention. They remain patient markers in a universe that prefers calm continuity. Another black hole that scientists study quietly is called TON 618. This black hole is very far away. So far that its light has traveled for a very long time to reach us. TON 618 is extremely large. Not in appearance but in mass. Yet even with this size, it does not disturb the universe around it loudly. It remains distant. Contained. Scientists learn from TON 618 how matter behaves when gathered over immense time. Not quickly, but patiently. It shows that even the largest black holes fit naturally into the structure of the universe. Another known black hole is NGC 1277. It rests inside a galaxy that appears calm and compact. This black hole is unusually heavy compared to the size of its galaxy. Even so, the galaxy remains stable. Stars continue to move in ordered paths. This teaches scientists that balance can exist in many different forms. There is no single design. Black holes adjust to their surroundings, and surroundings adjust to them. There is also a quiet black hole called XTJ 1650-500. It was noticed because of subtle changes in light nearby. These changes were not sudden. They unfolded slowly. From these calm observations, scientists learned more about how matter settles near black holes. Another well-studied black hole is GROJ 1655-40. It exists with a companion star. The star releases material gradually. That material forms a soft, rotating disk. The disk does not fall inward at once. It circles. It waits. This system helps scientists understand how energy spreads. Without bursts. Without chaos. There is also Holmberg 15A, a galaxy with a very large black hole at its center. This black hole influences the galaxy gently. It does not tear it apart. It supports long-term structure. Scientists observe these systems over many years. No single moment explains everything. Patterns matter more than events. These named black holes are useful because they behave predictably. They allow ideas to be tested carefully, repeatedly. They confirm that gravity behaves the same, no matter where it is observed, whether nearby or unimaginably distant. Each black hole adds clarity, not excitement, not urgency, just understanding. As you listen, these black holes continue their slow existence. They do not change pace. They do not respond. They remain quiet examples of how the universe prefers stability over speed. There is a black hole known as S50014+81. It exists very far from Earth. So far that its light began its journey long before humans existed. This black hole is extremely massive. Yet it remains calm. Its influence spreads slowly across space. Scientists learn from S50014+81 how black holes can grow over immense time without disrupting their surroundings. Another black hole rests in the galaxy called IC 1101. This galaxy is very large, and at its center lies a black hole that helps hold it together. The galaxy moves slowly. Stars follow wide paths. Nothing collapses. Nothing rushes. This system shows that size does not require instability. Even very large structures can remain balanced. There is also a black hole called M60 UCD1. It exists in a compact group of stars. This black hole is heavy compared to the size of its surrounding system. Even so, the stars remain organized. They continue their quiet orbits. From this, scientists learn that black holes can exist in many different environments. They adapt without disruption. Another studied black hole is Swift J1357.2-0933. It is known for subtle changes in nearby light. These changes do not occur suddenly, they happen gradually. By watching these slow variations, scientists gain insight into how matter moves near black holes. The process is careful, measured. There is also NGC 4395, a small galaxy with a surprisingly active black hole. Despite this activity, the galaxy remains stable. This shows that even when black holes interact more often, balance can still be maintained. Scientists use these examples to compare different systems. By doing so, they confirm that gravity behaves consistently everywhere. Black holes do not depend on location. They do not change rules based on distance, whether in large galaxies or small clusters. The same calm principles apply. These named black holes are not unusual. They are representative. They quietly demonstrate that the universe values consistency. As you listen, these systems continue unchanged. Their motion remains slow. They do not hurry. They do not pause. They simply continue. One black hole that scientists often mention is A0620-00. It is not large when compared to others. Yet it is important. This black hole is relatively close to Earth. Its nearness allows careful observation. It shares space with a companion star. That star moves gently around it. By watching this slow orbit, scientists measure the black hole's mass. Not by force, but by motion. A 0620-00 shows that even small black holes follow the same calm rules as the largest ones. Another known black hole is LMCX1. It exists in a nearby galaxy. This black hole also has a companion star. Material moves gradually from the star toward the black hole. The movement is smooth, unhurried. Light produced by this process is steady. It does not flicker suddenly. From this, scientists learn how matter behaves when guided by gravity over long periods. There is also M33X7, a black hole in a neighboring galaxy. It is known for its regular orbit. Everything about this system is predictable. This predictability helps scientists test ideas. If theories are correct, motion should remain steady. And it does. Another black hole is GRS 1915+105. It has been observed for many years. Changes near this black hole occur slowly. Patterns repeat. From these repetitions, scientists learn how energy is released without disruption. Even when activity increases, it settles back into calm behavior. There is also NGC 3115, a galaxy with a quietly massive black hole at its center. This black hole influences star motion gently. The galaxy remains smooth and ordered. These systems show that black holes do not need isolation. They exist within communities of stars. They interact without conflict. Scientists value these black holes because they behave consistently. No matter where they are found, their influence follows the same principles. This consistency builds confidence. Understanding becomes stronger. Knowledge accumulates quietly. As you listen now, these black holes continue their steady paths. They do not respond to attention. They do not accelerate. They do not pause. They remain part of the universe's slow rhythm. Some black holes are not widely discussed. Not because they are unimportant, but because they behave quietly. One such black hole is XDJ 1118+480. It exists high above the plane of the Milky Way. Its position suggests a long journey. Over time, it moved away from where it first formed. Even this movement was slow, guided by gravity. By studying this black hole, scientists learn how black holes can travel through galaxies. Not quickly. Not forcefully. Another black hole is Maxi J1820+070. It was observed over many months. During this time, changes in light occurred gradually. Patterns formed. These patterns help scientists understand how material settles near a black hole. Nothing happens suddenly. Every change followed a steady rhythm. There is also V4641 Sagittarii. It shares space with a companion star. Material moves slowly between them. Gravity guides the flow. This system teaches how mass exchange does not require instability. Balance can remain. Another quiet system is GS 2000+25. It has been observed for decades. Over that time, its behavior has remained consistent. This consistency allows long-term study. Knowledge accumulates without interruption. There is also GRO J0422+32, a small black hole with a calm orbital system. Its companion star follows a predictable path. Nothing changes abruptly. This reinforces a simple idea. Black holes do not introduce chaos. They follow structure. Scientists compare these systems to understand similarities. Despite differences in size or location, the same rules apply. Gravity behaves the same. Space responds the same. Time adjusts the same. Black holes do not vary their nature. They remain consistent examples of universal laws. This reliability is valuable. It allows understanding to grow steadily. These lesser-known black holes do not seek attention. They do not stand out. Yet they quietly confirm that the universe prefers order over disruption. As you continue listening, these systems remain unchanged. Their motion stays slow. They exist without urgency, without demand. They simply continue, aligned with the universe's calm design. Some black holes are studied because of how long they remain stable. They do not change quickly. They hold their patterns over time. One such black hole is H1743-322. It has been observed across many years. During this time, its behavior has followed familiar cycles. Light changes slowly. Energy spreads evenly. These repeating patterns help scientists understand how matter adjusts to gravity, without sudden movement. Another calm system is 4U1543-47. This black hole exists with a companion star. The star releases material gently. The black hole accepts it gradually. Nothing rushes inward. Nothing is forced. This system shows how interaction does not require instability. There is also XTJ1550-564, a black hole observed during long periods of activity. Even when changes occur, they unfold over time. Scientists focus not on moments, but on trends. These trends reveal how energy moves calmly through space. Another system is GRS 1009-45. It has been watched quietly for decades. Over that time, its behavior has remained predictable. Predictability allows trust. Trust allows understanding. There is also Swift J1753.5-0127, a black hole known for steady emissions. Its output does not spike suddenly. It remains smooth. This smoothness helps confirm that black holes regulate energy naturally. Scientists also study LMCX3, a black hole in a nearby galaxy. Its motion and influence are gentle. Its environment remains calm. These systems are valuable because they do not surprise. They demonstrate that black holes prefer balance. By comparing many such systems, scientists confirm a consistent pattern. Black holes behave the same, regardless of location. Distance does not change the rules. Time does not change the rules. Only patience reveals them. As you listen now, these black holes continue their steady existence. They do not accelerate. They do not slow unexpectedly. They follow the universe's quiet memory. Everything remembers its path. Everything repeats gently. Nothing is lost. Nothing is rushed. Black holes exist in many kinds of places. Some are in large galaxies. Some are in smaller systems. One black hole studied quietly is NGC 4051. It sits in a galaxy that appears calm and orderly. This black hole shows gentle activity. Light changes slowly. Energy moves without disruption. Scientists observe it over long periods. They look for consistency rather than events. Another system is NGC 4151, a galaxy with a well-studied central black hole. This black hole influences star motion subtly. Nothing collapses. Nothing rushes. Its behavior helps scientists understand how black holes coexist with surrounding matter. There is also NGC 4258, known for its precise measurements. Gas clouds near its black hole move in smooth paths. Their motion is highly regular. From this regularity, scientists measure distance and mass with great confidence. This black hole acts like a reference point. Reliable. Stable. Another example is NGC 4395, a small galaxy with a modest black hole. Despite its size, the black hole behaves predictably. This shows that scale does not change behavior. Small or large, the same calm rules apply. There is also NGC 3783, where scientists study light responding to gravity. Changes appear as gentle delays, not sudden shifts. These delays help confirm that light follows curved paths in space. Black holes in different environments do not act differently. They adapt without disturbance. By studying many galaxies, scientists confirm that black holes fit naturally into cosmic systems. They are not intruders. They are components. They support structure rather than threaten it. These observations are gathered slowly. Data accumulates quietly. Years pass. Understanding grows. As you continue listening, these black holes maintain their steady presence. They do not demand attention. They simply remain where they are, following the same quiet laws that guide the rest of the universe. Some black holes are valuable because of how long they remain unchanged. They act like quiet records of cosmic history. One such black hole is found in NGC 4593. It sits calmly at the center of its galaxy. Light from nearby regions changes slowly. These changes repeat in familiar patterns. From this repetition, scientists learn how gravity affects time and motion together. Another well-studied system is NGC 5548. Its central black hole has been observed for decades. Over this long time, its behavior has remained consistent. This consistency allows scientists to track how light responds to curved space without interruption. There is also NGC 6814, a galaxy with a quietly active black hole. Light near this black hole shows gentle delays. These delays match predictions. This confirms that gravity shapes time calmly and precisely. Another example is NGC 7469. Its black hole exists within a structured environment of stars and gas. Nothing moves suddenly. Everything follows smooth paths. Scientists observe this system to understand how black holes coexist with ongoing star formation. There is also NGC 1068, a galaxy whose central black hole is hidden behind dust. Even without direct visibility, its presence is known through motion and light behavior. This shows that black holes do not need to be seen to be understood. Their influence remains steady and measurable. Another quiet black hole resides in NGC 3227. It interacts gently with nearby matter. Energy moves gradually. Nothing destabilizes. By comparing all these systems, scientists learn that black holes preserve information over time. They do not erase history. They record it through structure and motion. Each orbit, each delay, each pattern adds to a long archive of data. This archive is not stored intentionally. It exists naturally. The universe remembers itself through motion. Black holes are part of this memory. They do not change quickly. They allow time to leave traces. As you listen now, these traces continue to form quietly. Nothing is rewritten. Everything follows the same calm sequence, moment after moment, without urgency. Black holes interact with matter in calm, predictable ways. They do not pull suddenly. They allow matter to respond gradually. One well-studied system is NGC 3516. Its central black hole influences nearby gas clouds. These clouds do not fall inward quickly. They move in wide, smooth paths. Light from this region changes slowly. These changes help scientists understand how matter adjusts to curved space over time. Another quiet system exists in NGC 3783. Here, gas moves gently around the black hole. Its motion creates patterns that repeat. These repetitions allow careful measurement. Nothing about this system feels unstable. Everything follows expected paths. There is also NGC 7213, a galaxy with a calmly active black hole. Energy near the center spreads evenly. Light remains steady. This system shows that black holes can interact without disrupting their surroundings. Another example is NGC 4593, where long-term observation has revealed consistency. Patterns do not break. They continue across years. This long memory allows scientists to test ideas without rushing. There is also NGC 7469, where star formation exists near a black hole. Even here, balance is maintained, stars form, gas moves. The black hole remains steady. Nothing interferes abruptly. Black holes also help scientists understand how matter cools. As matter moves away, energy disperses calmly. This slow cooling prevents sudden collapse. Another system, NGC 3227, shows how black holes and stars coexist peacefully. Gravity guides movement. Space provides distance. No force dominates. By studying many such systems, scientists confirm that black holes are not destructive by nature. They are regulators. They guide motion through consistency. They allow matter to find stable paths. These lessons apply everywhere in the universe, not just near black holes. The same rules guide planets, stars, and galaxies. Black holes simply make these rules visible. As you listen, matter continues its slow movement across space. Energy spreads gently. Nothing demands attention. Nothing accelerates suddenly. Everything follows the universe's quiet rhythm. Not all massive stars become black holes. Some follow a slightly different path. These stars become neutron stars. Neutron stars are formed from stars that were heavy, but not heavy enough to collapse completely. Instead of becoming a black hole, the star compresses into something very small and dense, very stable. A neutron star still has a surface. It still exists as an object you could point to. A black hole does not. This difference is important. Not dramatic. Just structural. Neutron stars hold themselves up through internal balance. Black holes pass that limit and continue collapsing inward. Both follow the same natural laws. They simply stop at different points. Neutron stars can rotate slowly, steadily. Some rotate with remarkable regularity. Their motion becomes predictable. Black holes can also rotate, but their rotation affects space itself, gently shaping motion nearby. Neutron stars can release energy quietly, in steady patterns. Black holes do not release light directly. They influence what happens nearby instead. This difference helps scientists understand how gravity behaves under different conditions. Neutron stars are extremely dense, but space still behaves normally around them. Near black holes, space curves more deeply. Time slows slightly more. Paths bend more noticeably. These differences are gradual, nothing sudden. By comparing black holes and neutron stars, scientists refine their understanding of limits. They learn how much mass space can support before behavior changes. Neutron stars mark one boundary. Black holes mark the next. Neither is wrong. Neither is dangerous by nature. They are outcomes. Both objects often exist in calm systems. They can have companion stars. Matter moves slowly around them. Nothing rushes inward. This comparison also helps scientists understand why black holes are rare. Not every star becomes one. Only the most massive pass the final threshold. Most stars end quietly, without collapse. This shows that the universe prefers balance. Extreme outcomes are uncommon. Neutron stars and black holes both demonstrate restraint. They follow rules without exception. They show that nature does not exaggerate. It transitions slowly. By studying both, scientists see the full range of stellar endings, from quiet fading to dense stability to deep gravitational stillness. Each stage fits naturally into cosmic order. As you listen now, these objects continue their steady existence. Neutron stars rotate calmly. Black holes remain still. Neither seeks attention. Neither creates urgency. They simply exist as different expressions of the same patient universe. Many ideas about black holes come from stories and films. These ideas are not meant to be harmful. They are simply exaggerated. One common myth is that black holes act like cosmic vacuum cleaners, that they pull everything nearby inward. This is not how black holes behave. From a distance, a black hole's gravity feels no different than the gravity of any other object with the same mass. If the Sun were replaced by a black hole of the same mass, the planets would continue their orbits calmly. Nothing would suddenly fall inward. Gravity depends on distance, not on mystery. Another myth is that black holes are constantly consuming matter. In reality, most black holes are inactive. They do not absorb stars regularly. They spend long periods doing nothing at all. Matter only moves inward if it comes very close. And most of space is empty. Another common idea is that black holes are dangerous to the universe, that they threaten everything. In truth, black holes are rare. They occupy very small regions of space. The universe is mostly quiet and empty. Distance keeps everything safe. Another myth suggests that black holes are holes in space, that they are empty voids. Black holes are not empty. They contain mass. Very concentrated mass. They are objects, not openings. Some people imagine black holes as spinning tunnels, paths to other places. This idea is not supported by observation. Black holes behave predictably. They do not act as gateways. Another myth is that time stops completely near a black hole. Time does slow slightly, but it does not freeze. Time continues calmly, just at a different pace. There is also a belief that nothing can be learned from black holes, because they cannot be seen. Yet much has already been learned. Through motion, through light behavior. Observation does not require direct vision. It requires patience. Some believe black holes are violent by nature. In truth, they are passive. They respond. They do not attack. Even when matter moves nearby, the process is gradual. No sudden destruction occurs. Another idea is that black holes break the laws of physics. In fact, they follow those laws precisely. They do not ignore rules. They demonstrate them clearly. Finally, there is a myth that black holes represent endings. They are not endings. They are stages. They exist within the universe's long story, not outside it. By clearing these myths, black holes become easier to understand, less dramatic, more calm. They return to what they truly are: quiet results of gravity and time, working patiently together. There is another common belief that black holes grow endlessly, that once they exist, they must become larger and larger. In reality, black holes grow very slowly. They do not pull matter from far away. They only gain mass when something passes extremely close. Most black holes spend their lives unchanged. Years pass. Centuries pass. Nothing happens. Growth is rare, not constant. Another idea suggests that black holes move around hunting stars. This is not how motion works in space. Black holes move the same way stars do. They follow orbits. They drift with galaxies. They do not chase. They do not aim. Motion in space is calm and predictable. Some imagine that black holes are unstable, that they could suddenly collapse or explode. Black holes are among the most stable objects in the universe. Once formed, they remain steady for immense periods of time. They do not change suddenly. They do not fail. Another misunderstanding is that black holes destroy information. What actually happens is more subtle. Information becomes difficult to reach, not erased. The universe does not forget easily. Black holes hide information behind distance and time. They do not remove it from existence. Another belief is that black holes are loud events, that they produce noise. Space does not carry sound. Black holes are silent by nature. Everything that happens near them happens without sound. No echoes. No crashes. There is also a myth that black holes twist reality into chaos. In truth, they create structured, predictable behavior. Paths curve smoothly. Time adjusts gently. Nothing becomes random. Some think black holes represent failure in physics, places where understanding ends. In fact, they are places where understanding becomes more careful. They test ideas slowly. They refine knowledge. Another myth is that black holes are unique monsters, separate from everything else. They are not separate. They are part of the same continuum. That includes stars, planets, and galaxies. They follow the same laws. Black holes are not exceptions. They are confirmations. They show that even under extreme conditions, the universe remains calm. Nothing breaks. Nothing panics. As these myths fall away, what remains is something quieter. Black holes become easier to accept, easier to understand. They return to their true role. Not as threats, not as mysteries beyond reach, but as steady outcomes of gravity and time, working without urgency. Another idea that often appears is that black holes are mistakes, that the universe somehow went wrong when they formed. In reality, black holes are expected outcomes. They appear when gravity follows its path completely. Nothing unusual happens. Nothing breaks. Another myth suggests that black holes should be everywhere, that space should be full of them. This is not the case. Only very massive stars can form black holes. Most stars are not heavy enough. Most stars end their lives quietly. They fade. They cool. This rarity makes black holes special, but not threatening. Some believe black holes make space unstable, that their presence weakens reality. Space remains strong. It adapts smoothly. Black holes fit into space. They do not damage it. Another idea is that black holes pull things from very far away. That distance does not matter. Distance matters greatly. Gravity weakens with space. Far away, its effect is gentle. This is why galaxies remain stable. This is why planets stay in orbit. Some imagine black holes as active destroyers, always doing something. Most black holes are inactive. They remain silent for their entire existence. They are still. There is also a belief that black holes mean the universe is dangerous. In truth, the universe is mostly empty, calm. Black holes occupy tiny regions. They do not dominate space. Another myth suggests that black holes are unpredictable. They are among the most predictable objects known. Their behavior follows clear rules. This predictability allows careful study. Some think black holes represent the limits of understanding, that nothing more can be learned. Yet every year, understanding improves. Slowly. Black holes reward patience. They do not hide knowledge. They reveal it gradually. When all myths are removed, black holes become quieter, less dramatic, more understandable. They return to their true nature. Not monsters, not accidents, but calm results of gravity, time, and space, working together without urgency. The event horizon is often misunderstood because it sounds like a solid edge, but it is not a surface. There is nothing physical there. No wall. No boundary you could touch. It is simply a region where space behaves differently. If someone were far away, watching an object move toward a black hole, they would see it slow down. The movement would appear gentle, gradual. The object would never seem to cross the horizon. It would fade quietly. This does not mean it stops. It means time appears different from a distance. For the object itself, nothing unusual would happen at the horizon. No shock. No sudden pull. The crossing would feel ordinary. Space would continue guiding motion calmly. The event horizon grows only if the black hole gains mass. It does not expand on its own. It does not jump outward. Small black holes have small horizons. Large black holes have wider ones. A larger horizon is gentler. Space curves slowly. This means that size brings calmness, not danger. The event horizon is invisible because it does not reflect light. There is no surface to shine. Light simply follows space and continues inward. This invisibility is not hiding, it is absence of reflection. The event horizon is stable. It does not flicker. It does not vibrate. It remains where gravity places it. It also does not affect distant space. Only its immediate region is involved. Planets, stars, and galaxies far away continue undisturbed. The event horizon teaches that boundaries can exist without violence, that limits can be smooth. It shows how the universe marks transitions quietly. As you listen now, event horizons remain where they are. They do not move toward anything. They wait. They exist as calm markers of where space gently changes behavior, nothing more. Black holes are not completely silent forever. Over extremely long periods of time, they change. This change is called Hawking radiation. It does not involve light bursting outward. It does not create sound. It is an extremely gentle process. Near the event horizon, space itself is not empty. It has small fluctuations. These fluctuations are calm. They appear and fade naturally. Over immense time, a tiny amount of energy can drift away from the black hole. This does not happen quickly. It is not noticeable. For large black holes, this process is incredibly slow, so slow that the universe barely registers it. A black hole does not shrink suddenly. It loses mass gradually. Years pass. Then millions of years. Then far more. Hawking radiation does not threaten anything. It does not affect nearby space. It is spread thinly across time itself. This idea shows that black holes are not eternal, but their endings are quiet. No explosion, no collapse, just a slow release of energy, so gentle that it feels like stillness. Hawking radiation teaches that nothing in the universe is truly fixed. Everything changes, but at its own pace. Even the most massive black holes follow this rule. This process will outlast stars, planets, and galaxies. It belongs to a future far beyond imagination. As you listen now, Hawking radiation is not happening here. It is part of a very distant time. This moment remains calm, undisturbed. The universe continues its slow rhythm. Black holes continue theirs. Nothing rushes. Nothing ends. Hawking radiation is not something that happens suddenly. It is not an event. It is a process. A very slow one. To understand it calmly, it helps to remember that empty space is never truly empty. Even in the quietest regions of space, tiny changes appear and disappear. They are brief. They are gentle. Near the event horizon, these tiny changes behave slightly differently. Over immense time, a small amount of energy can move away from the black hole. This energy is not pulled outward. It is not pushed. It simply drifts. This drift is what we call Hawking radiation. It does not glow. It does not shine. It spreads so slowly that it blends into the background of the universe. For very large black holes, this process is almost invisible. So slow that billions of years pass without noticeable change. A black hole losing mass this way does not shrink in any visible sense. It remains steady, stable. Only over unimaginable stretches of time does the change become meaningful. This teaches something important. Even when change exists, it does not have to be noticeable. The universe allows quiet change. Hawking radiation also shows that black holes are not separate from time. They follow it. They do not escape change. They participate in it, but they do so patiently. This process does not disturb nearby stars. It does not affect galaxies. It is too gentle to influence anything nearby. Space remains calm. Hawking radiation also helps scientists understand how energy behaves at the smallest scales. It connects gravity with very subtle processes. Not loudly, not dramatically, just enough to reveal consistency. The idea of Hawking radiation does not suggest destruction. It suggests balance. Energy is never trapped forever, but it is also never released quickly. The universe prefers smooth transitions. For small black holes, this process would happen faster. But small black holes are rare. Most black holes are large. And large black holes change slowly. This means that most black holes will remain present for far longer than stars. They will outlast galaxies. Only when the universe itself has grown very old will Hawking radiation become significant. Even then, the change will be quiet. No sound. No flash. Just a gentle fading. This idea replaces fear with patience. It shows that endings in the universe do not arrive suddenly. They arrive softly. Hawking radiation reminds us that permanence is not required for stability. Things can last and still change. As you listen now, Hawking radiation remains only a distant concept. It is not active here. It is not relevant to this moment. This moment is still. This moment is safe. The universe continues its long rhythm. Black holes continue theirs. Change happens, but only at the pace the universe prefers. Black holes often feel frightening because they are misunderstood. In reality, they pose no danger to Earth. The reason is simple. Black holes are very far away. Distance matters in the universe. Gravity weakens with distance. Even strong gravity becomes gentle when space is wide. The nearest known black holes are thousands of light years away. That distance is enormous. At such distances, their gravity has no effect on Earth. They cannot pull planets. They cannot disturb orbits. Earth continues its path, as it always has. There is also no hidden black hole. Moving toward our solar system, space is mostly empty. Movement is slow. Objects follow predictable paths. If a black hole were near Earth, its presence would already be known. Stars would move differently. Light would bend in noticeable ways. Nothing like this is observed. Another common worry is that Earth could suddenly fall into a black hole. This cannot happen. Falling requires closeness. Closeness requires travel. There is no mechanism for Earth to drift toward a distant black hole. Our solar system is stable. The sun's gravity holds the planets calmly. Nothing interferes. Even if the sun itself were replaced by a black hole of the same mass, Earth would continue its orbit, almost unchanged. This shows that black holes are not special threats. They obey the same gravitational rules as all other objects. Another concern is that black holes could grow and reach us. Black holes do not expand outward. They grow only when matter comes very close. Most of space has nothing to offer them. They cannot stretch across the universe. They remain local objects. The universe itself is expanding. This expansion increases distance. It makes interaction even less likely. Black holes also do not emit anything harmful. They do not radiate danger. They remain silent. Even Hawking radiation is far too weak to matter on human timescales. It does not reach us. All of this means that black holes exist peacefully within the universe. They are not predators. They are not moving hazards. They are simply outcomes of gravity and time. As you listen now, Earth remains safe. The night sky remains calm. Black holes stay where they are. Nothing approaches. Nothing accelerates. The universe continues its quiet balance. Black holes may feel distant, but the ideas learned from them apply much closer to home. They help explain how gravity works everywhere. Gravity is not only about pulling objects. It is about shaping space. This idea is used daily. Satellites orbit Earth by following curved paths in space. Not by force, but by balance. The same principles that guide stars around black holes also guide satellites around Earth. Time behaves slightly differently in different gravitational conditions. This is not noticeable in daily life, but it matters for technology. GPS satellites rely on precise timekeeping. Their clocks run at a slightly different pace than clocks on Earth. This difference is predicted using the same understanding of gravity that comes from studying black holes. Without correcting for this effect, GPS would slowly become inaccurate. Black holes help confirm that these time adjustments are real. They show that time is flexible. It adapts to gravity calmly. The same calm rules apply whether gravity is strong or gentle. Black holes also help scientists understand motion. Objects move along paths shaped by space itself. This idea is used when planning spacecraft trajectories. Spacecraft do not travel in straight lines. They follow curved routes, guided by gravity. This guidance is predictable. It allows precise navigation. Black holes simply make these effects easier to see. Even the idea of energy balance comes from the same foundation. Energy spreads smoothly. It does not appear or vanish suddenly. This principle applies from power systems on Earth to stars and black holes in space. Black holes also help refine measurement tools. By studying extreme conditions, scientists test the limits of instruments. These improved tools benefit many areas of science: medical imaging, communication systems, and navigation. All rely on accurate measurements of time and space. Understanding black holes strengthens confidence in these measurements. It shows that physics behaves consistently. The universe does not change rules based on scale. Small systems and large systems follow the same calm principles. This consistency allows technology to work reliably. As you listen now, everyday systems continue operating quietly. Clocks remain synchronized. Satellites remain in orbit, all guided by the same gentle rules that shape black holes far away. Nothing special is required. Nothing extraordinary. Just patience, balance, and consistency. The universe provides these freely. Long before galaxies looked the way they do today, the universe was quieter and simpler. In those early times, matter was spread more evenly. Movement was slow. Small differences gradually grew. Some of the first stars were much larger than stars we see now. They lived briefly. They ended calmly. From these early stars, the first black holes formed. They were not dramatic. They did not dominate space. They simply remained where gravity placed them. Over time, these early black holes became gathering points. Gas moved slowly toward them, not rushing, just drifting. This gentle movement helped shape the first galaxies. Black holes did not create galaxies. They supported their structure. As matter settled, stars formed nearby. Systems organized themselves naturally. The universe preferred order over chaos. Early black holes grew gradually, not by pulling from far away, but by accepting matter that passed close. This slow growth allowed galaxies to remain stable. Light from these early systems traveled for immense time before reaching us. By observing it today, scientists look back into the universe's past. These observations show that black holes existed early, but quietly. They were part of the foundation, not interruptions. As galaxies matured, black holes remained at their centers. They did not control motion. They guided it gently. Stars continued to form. Galaxies continued to rotate. Nothing collapsed suddenly. The early universe was not violent. It was patient. Black holes fit naturally into this patience. They were present, but not overpowering. By studying distant galaxies, scientists see the same patterns repeated across time. Black holes always behave consistently. This consistency confirms that the laws of physics were the same long ago as they are now. Nothing changed abruptly. The universe grew older without losing balance. As you listen now, this ancient time remains far away. It does not affect this moment. The early universe continues, only as quiet light reaching us. Black holes from that time still exist. unchanged in nature, steady in role. They remain part of a long story that moves slowly, without urgency. As the early universe expanded, space slowly grew wider. Matter became more spread out. Even then, black holes remained patient. They did not pull the universe inward. Expansion continued calmly. This balance between gravity and expansion allowed structure to form, without collapse. Early black holes helped organize motion nearby. Gas clouds followed curved paths. Stars formed along these paths. Nothing moved suddenly. This slow organization created patterns, spiral shapes, elliptical forms. These shapes are still seen today. Black holes did not design these patterns, they allowed them to settle. As galaxies grew older, black holes at their centers remained steady reference points. Stars adjusted their orbits slowly. Galaxies rotated smoothly. Time passed quietly. Some early black holes merged with others. This did not happen often. And when it did, it unfolded gradually. Space adjusted gently. Energy spread outward softly. No disturbance traveled far. These slow mergers helped black holes grow, without disrupting their surroundings. Over billions of years, some black holes became very large. Even then, their influence stayed local. Galaxies did not lose shape. They gained stability. The early universe did not rush toward complexity. It allowed it to emerge. Black holes participated in this emergence. Without control. They were part of the environment, not drivers of chaos. By observing very distant galaxies today, scientists see black holes already in place. This tells us that black holes were present early, but quietly. They did not appear suddenly later. They grew alongside everything else. This shared growth explains why galaxies and black holes are so closely linked, not through dominance, but through coexistence. The universe prefers cooperation. As matter cooled, as light traveled farther, as space expanded, black holes continued their steady roll. They did not speed things up. They did not slow things down. They remained where gravity placed them. This long continuity shows that black holes are not interruptions. In cosmic history, they are threads. Threads that run through time, without pulling too tightly. As you listen now, this early universe remains distant. Its events are finished. Its light continues traveling. Black holes from that time still exist somewhere, unchanged in nature, unchanged in behavior, quiet witnesses to a universe that learned to grow by moving slowly. Black holes are not studied through direct contact. They are studied through patience. Scientists do not rush observations. They watch slowly. Modern telescopes collect light over long periods of time, sometimes months, sometimes years. This light is faint. It arrives gently. By comparing small changes, patterns begin to appear. These patterns reveal motion. They reveal structure. Scientists also observe how stars move near invisible centers. These movements are steady. Orbits repeat. Paths remain smooth. From these repeated motions, mass can be estimated. Distance can be understood. Nothing is guessed quickly. Radio telescopes listen to quiet signals. Not sound, but waves that travel silently through space. These signals pass through dust and gas, without disturbance. They reveal hidden regions. Optical telescopes collect visible light. Infrared instruments collect warmth. Each method adds a layer. No single observation is enough. Understanding grows by accumulation. Computers help organize this information. They simulate motion slowly. Simulations are not predictions of drama. They are tests of consistency. If models match observation, confidence increases. If they do not, models are adjusted calmly. This process repeats. Scientists also collaborate quietly. Data is shared. Results are compared. Disagreement is not conflict. It is refinement. Black hole research moves forward through calm verification. No discovery changes everything at once. Each adds a small piece. Space-based telescopes avoid interference. They observe without atmosphere. Ground-based telescopes wait for clear nights. They do not force observation. Timing matters. Patience matters. Some observations take decades to complete. This long timescale matches the nature of black holes themselves. They do not change quickly. They reward careful study. As you listen now, scientists continue their work quietly. They wait. They observe. They compare. Nothing is rushed. Understanding grows at the same pace the universe prefers. Black holes do not reveal themselves suddenly. They allow understanding slowly. And science follows that invitation without urgency. Even after many years of study, black holes continue to offer quiet questions. Not mysteries that demand answers, but areas where understanding can deepen slowly. Scientists want to learn more about how black holes grow over long periods. Not through rare events, but through everyday calm interaction with matter. They also study how black holes influence galaxies over billions of years. This influence is subtle. It does not act through force, but through balance. Another area of interest is how black holes connect gravity and quantum behavior. These ideas are explored carefully. No assumptions are rushed. Scientists use black holes to test whether existing theories remain consistent. Under extreme conditions, they look for quiet mismatches, small differences. If found, theories are refined. Another goal is to improve observation, to see details more clearly. This does not require speed. It requires sensitivity. Future instruments are designed to detect even softer signals, signals that are already present, but currently difficult to notice. Scientists also hope to understand how black holes formed in the earliest universe. They compare distant observations with calm simulations. These comparisons reveal trends, not sudden truths. Another focus is understanding mergers, not as dramatic collisions, but as long processes. Mergers unfold over time. Space adapts gently. By studying these processes, scientists learn how structure evolves. They also seek to understand how black holes eventually fade, not as endings but as transitions. These studies require patience, far beyond individual careers. Knowledge passes between generations. This slow continuity matches the subject itself. Black hole research is not driven by urgency. It is driven by consistency. Every answer raises calmer questions. Nothing demands immediate resolution. As you listen now, these future studies are already beginning. Observations are being collected. Data is being stored. Understanding will come in its own time. Black holes will remain unchanged. While curiosity continues, they do not resist study. They simply wait. And science waits with them. Why humans continue to study black holes? Black holes do not ask to be studied. They do not send signals. They do not invite attention. Yet humans continue to observe them. This curiosity does not come from urgency. It comes from patience. Humans look at black holes, not to control them, but to understand how the universe behaves. When it is left alone, black holes represent places where nature follows its rules completely. Nothing interferes. Nothing interrupts. By studying them, humans learn how systems behave, without design or intention. This knowledge applies everywhere. Curiosity about black holes is not driven by fear. It is driven by calm interest. They are distant enough to feel safe, yet clear enough to reveal patterns. Humans study black holes because they are consistent. They do not change unexpectedly. They do not respond emotionally. They allow understanding to build slowly. This slow pace matches how human knowledge grows. No single discovery explains everything. Understanding accumulates. Black holes remind humans that not all answers need immediacy. Some understanding takes generations. People who study black holes often know they will not see final results. They contribute small pieces, carefully. This willingness reflects something deeper. Humans value knowledge, even when it does not solve immediate problems. Studying black holes does not change daily life quickly, yet it strengthens understanding of how reality works. This understanding builds confidence. It shows that the universe is not chaotic. Even in extreme conditions, patterns remain. Humans also study black holes because they challenge imagination gently. They stretch understanding without overwhelming it. They invite thought without demand. This balance is rare. Black holes do not promise reward. They offer clarity. They show that complexity can exist quietly. That power does not require noise. As humans observe black holes, they also learn about themselves. They learn patience. They learn humility. They learn that knowledge does not have to be urgent to be meaningful. As you listen now, human curiosity continues calmly. Questions remain open. Observation continues. Black holes remain unchanged. Understanding moves slowly forward. Nothing rushes. Nothing concludes. The universe remains open to thought, and thought remains open to the universe. Black holes and the far future of the universe. The universe is not in a hurry. It moves on timescales that are difficult to imagine. Stars shine for long periods. Galaxies rotate slowly. Black holes remain present through all of this. As the universe grows older, stars will gradually use their fuel. They will cool. They will fade. This process takes immense time. Long after most stars have dimmed, black holes will still remain. They do not rely on light. They do not depend on fuel. They persist quietly. The space between galaxies will continue to expand. Distances will grow. Interactions will become rarer. In this quieter universe, black holes will be among the most stable objects left. They will not change suddenly. They will not move quickly. They will continue their slow relationship with time. Over extremely long periods, Hawking radiation will continue its gentle work, not as an event, not as a signal, just as a gradual shift. This process will take longer than the current age of the universe. During this time, nothing dramatic happens. Black holes do not announce change. They do not mark moments. They fade quietly, if they fade at all. The far future of the universe is not filled with activity. It is filled with stillness. Motion slows. Energy spreads thinly. Black holes fit naturally into this calm environment. They do not resist change. They do not accelerate it. They follow the same rules that have always guided them. Even in the far future, the universe remains structured. Not busy. Not empty. Just quiet. Black holes in this future do not dominate space. They remain local objects. The universe does not collapse toward them. Expansion continues. Space grows. Time continues. This long future is not something to imagine actively. It is too distant. Too slow. It exists beyond urgency. As you listen now, this future has no effect on the present. The present remains calm. Black holes remain far away. The universe continues its slow, steady rhythm. Nothing approaches. Nothing ends. Everything simply continues moving forward at the pace the universe has always preferred. How black holes change the way time is felt. Time does not move at the same pace everywhere. This idea feels unfamiliar, but it is calm and consistent. Near strong gravity, time moves slightly more slowly. Black holes help scientists observe this clearly. The closer something is to a strong gravitational field, the more time adjusts. This adjustment is smooth, not sudden. There is no moment when time stops. It continues calmly, just at a different rhythm. Far from a black hole, time flows as expected. Near it, clocks would tick more slowly. This difference is not noticeable in daily life. but it matters over long periods. Black holes show that time is connected to space. When space curves, time responds. This relationship explains why time behaves differently in different places. Black holes do not cause confusion. They reveal structure. Time near a black hole is not broken. It remains ordered. Events still happen. Processes continue. They simply take longer. From an outside perspective, for someone far away, movement near a black hole appears slowed. Light seems delayed. For the object itself, time feels normal. This difference in perspective is a natural result of gravity affecting time. Black holes help scientists test these ideas carefully. Observations match predictions closely. This consistency confirms that time is flexible, but reliable. The same principles apply to smaller systems. Even near Earth, time behaves slightly differently at different heights. This effect is tiny, but measurable. It is corrected for in everyday technology. Black holes make this effect easier to see, but they do not create it. They simply magnify it. Time remains calm, even under extreme conditions. It does not collapse. It does not rush. Black holes teach that time is not absolute. Yet it is not chaotic either. It follows gentle rules. As you listen now, time continues to pass normally. Nothing here changes pace. The universe allows different rhythms, without conflict. Black holes remain distant examples of how time adapts, without losing order. Everything continues in its own calm sequence. Black holes and the quiet nature of space. Black holes are often imagined as loud and violent. In reality, they exist in complete silence. This silence is not created by black holes. It comes from space itself. Sound needs a medium to travel. Air, water. Space has none of these. Because of this, nothing in space produces sound the way it does on Earth. Even the largest events happen without noise. Black holes do not roar. They do not echo. Everything that happens near them happens quietly. Matter moving toward a black hole does not crash. It moves smoothly. There are no shock sounds, no collisions that could be heard. The silence around black holes is not emptiness. It is stillness. Energy moves. Light travels. But sound does not. This silence helps scientists study black holes. Nothing interferes. Signals arrive cleanly. Light reaches telescopes without distortion from sound. The quiet of space preserves information. Black holes fit naturally into this silence. They do not disturb it. They remain silent observers within a silent universe. Even when black holes interact with matter, the process is quiet. Energy spreads gently. Space absorbs movement without noise. This silence also affects how time is felt. Without sound, events feel slower. Motion feels smoother. Black holes emphasize this effect. They exist in regions where nothing announces itself. Everything simply occurs. The absence of sound does not mean absence of activity. It means activity without disturbance. This quiet allows the universe to maintain balance. No vibrations travel far. Nothing shakes distant systems. Black holes remain isolated in their influence. Silence protects structure. As you listen now, this silence exists around you metaphorically. There is no need for noise. The universe functions without it. Black holes remind us that not everything needs sound to be real. Some of the most powerful processes happen quietly, without announcement, without interruption. Everything continues in the calm background of space, where silence is not emptiness, but stability. Black holes and the scale of the universe. Black holes help place everything into perspective. They remind us how large the universe truly is. Even the biggest black holes occupy very small regions compared to galaxies, and galaxies themselves are small when measured against the full universe. This scale keeps interactions gentle. Distance creates calm. Black holes rarely affect anything beyond their immediate surroundings. Space provides room. The universe is mostly empty. This emptiness is not lack. It is balance. Scale prevents chaos. Black holes exist within this balance. They do not dominate it. Their influence fades with distance. This fading allows systems to remain stable. Planets remain in orbit. Stars continue their paths. Black holes show that size does not mean control. A massive object can still be limited. Gravity follows rules. These rules apply everywhere. Black holes make these rules visible without changing them. Scale also affects time. Large systems change slowly. Black holes change over immense periods. This slow pace prevents sudden disruption. The universe prefers gradual change. Black holes reinforce this preference. They show that power does not require speed. Scale creates patience. Distance softens effects. Even light takes time to cross the universe. This travel time spreads information gently. Nothing arrives suddenly. Black holes contribute to this calm distribution. They do not send signals. They do not announce presence. They simply exist. Scale also shapes understanding. Humans observe only small portions of space. Black holes help connect these observations to larger patterns. They anchor understanding without pulling attention. They remain reference points in a vast system. As you listen now, scale continues to work quietly. Nothing nearby feels overwhelming. Everything fits into something larger. Black holes remind us that the universe is not crowded. It is spacious. That spaciousness allows stability. It allows calm. And within this calm, everything continues at the pace it was meant to. A quiet moment to let everything continue. The universe does not notice endings. It does not pause when something finishes. It continues at the same calm pace as always. Black holes remain where they are, far away, unmoving. They are not waiting. They are not responding. They simply exist, as they always have. Stars continue their slow paths. Galaxies turn gently. Space remains wide and open. Nothing changes suddenly. Nothing asks for attention. Time continues in its quiet way. One moment following another, without effort. There is no need to think about distance now. No need to imagine scale. Everything that was described can remain where it is. Understanding does not need to be held. It can rest. Thoughts can become lighter, softer. Breathing continues naturally. No direction needed. The universe is not watching. It does not expect awareness. Black holes do not notice curiosity. They do not respond to questions. They remain distant markers. In a universe that prefers calm motion, nothing here is urgent. Nothing is incomplete. The story does not stop. It simply moves on, beyond this moment, without needing to be followed. This moment is enough. This moment is steady. Everything else can continue on its own. There is nowhere to go. Nothing to remember. Only a quiet space where time keeps moving, slowly, evenly.